Hey folks, in this video we're going to talk about magnetic flux. Now let me first refresh your memory about electric flux. So for electric flux, that's the symbol, it's a capital F in Greek of phi. Electric was equal to the area integral, so it's a double integral of E dot dA. Okay. And then we had Gauss's law, which I'll come back to in a second, involving electric flux. Okay, well, it turns out that magnetic flux is defined exactly the same way. You have an area integral of B dot dA. Okay, now the units for this, okay, so you're taking magnetic field, which is in Tesla, times an area, which is meters squared. So if you wrote Tesla meters squared, you'd be fine. But actually, there's a unit for that. It's called a Weber, okay, or just a WB for short, okay. Now, I won't do a really simple example like here's an area, here's a B. We've done a lot of that with electric flux, so it's the same idea. You do have to worry about if there's an angle. So like if your field, your magnetic field would say points this way and your area is like this, okay, well, you have to worry about that angle there between the magnetic field and well, actually, not that area, but this area here between the area vector and the magnetic field, okay? But I will do an example that involves a little integration, all right? So let's say, and we'll kind of tie in some stuff from this chapter. So let's say you have a current carrying wire. Let's say the current's traveling upward, and I first ask you to draw the magnetic field around that wire. Well, hopefully by now you're able to quickly figure out that the magnetic field on this side of the wire is pointing out of the page, and it's going to get weaker as you get farther away, and the magnetic field on this side of the wire is pointing into the page, and that's going to also get weaker as you get farther away, okay? Well, let's calculate the magnetic flux through a rectangle that's over here, okay? And some dimensions, we'll call this A, that's the distance from the wire to the near part of the rectangle. We'll call the width of the rectangle B, and we'll call the length of the rectangle L, okay? And we're going to integrate this. Now, B, if you'll recall, is magnetic field created by that wire is equal to mu naught I over 2 pi r. So as we get farther from the wire, that's your radius. As you get farther from the wire, your magnetic field weakens. So we can't just take B times A here because the B changes as you go from left to right in that rectangle. So we have to figure out a dA to integrate, okay, and to add up. So you got two choices. You can pick either a vertical dA or a horizontal dA and just add up all your slices. Well, we're going to pick the vertical dA, and there's two reasons for that. First, there's a conceptual reason. Okay, so I'm going to erase the other one. So the conceptual reason is if I make that dA skinny enough, the magnetic field in there will be roughly constant, okay? So that's the more important of the two reasons. But the other reason is mathematical. The area of that rectangle is L times the width, which is dr. That's a differential, that's a difference in the radius from the beginning of that to the end of that. That's your dr, okay? And we want our area to be in terms of dr because we have an r in our magnetic field. So then we'll be able to integrate. You can't just integrate 1 over r, you have to integrate dr over r, okay? So our magnetic flux, in this case, would be the double integral of B, which is mu naught I over 2 pi r times dA, which is L dr. Okay, now by the way, I'll make another note. The magnetic field here is perpendicular to that area, okay? It's going into the area, or it's parallel to the area vector, okay? So we don't have to worry about it. Now, in this case, we only have one variable, so we only have to integrate once, okay? So I will pull out everything that's a constant. We have a mu naught's a constant, we have the I, we have the 2 pi, and we have an L in the numerator like so. And what are we actually integrating? We're integrating dr over r, and we're integrating that from A to A plus B. Okay, that's where our rectangle starts at A and it ends at A plus B. And so you get a real easy answer here. Okay, the magnetic flux equals the integral of dr over r is natural log of r, and if you evaluate that from A to A plus B, you would get the following. Okay, you get this, and then natural log of A plus B over A. So that would be your magnetic flux, and it would be in Webers. Okay. Now, I want to make one more note about magnetic flux. And we're going to use magnetic flux, by the way, a lot in our next chapter. In this chapter, we're kind of just introducing it and the idea of what it is. It's the amount of magnetic field lines that poke through this area right here, right? Just like electric flux would be the amount of electric field lines that poke through that area. But in our next chapter, we are going to use this a lot. We're going to use magnetic flux. So I want you to get used to calculating it now. Now, I want to make one more note. Electric flux is involved with Gauss's law. And if you recall, Gauss's law in electric fields, okay, is the following. The net electric flux leaving an enclosed surface, so that would be double integral with a loop, okay, is equal to E dot dA. And this equals Qn over epsilon naught, okay? And so we use this usually to calculate we use this to calculate electric fields, okay, usually, all right? So what's the analogous equation in magnetic fields? So what would be Gauss in magnetic fields? So we have the net magnetic flux leaving an enclosed volume. That would be V dot dA. Well, that would equal what over here? All right. Well, I'm going to show you two examples, and then hopefully you'll figure it out before I tell you. All right. So let's say here's the first example. Let's say I have a current carrying wire, and it makes a magnetic field, just like we did above. So there's your magnetic field on the right, looks like that, gets weaker as you go outward, right? On the left, it'd be dots, and gets weaker as you go outward, okay? Well, what if I drew a three-dimensional shape anywhere, an enclosed surface anywhere in this picture? So I'll just draw it here, like so. So I'm drawing a rectangular solid, but it could be anything, all right? What is the net magnetic flux leaving that rectangular solid? Well, if you think about it, the field lines are poking into this top surface here. I'll kind of highlight that. So here's our top surface. So magnetic field lines are poking into that, okay? But then they're coming out that bottom surface down there. Every field line that pokes into the top surface pokes out of the bottom surface, okay? You won't have any field lines poking in or out of this or that surface. The left-hand surface over here and the right-hand surface over there, you'll get maybe a little field poking in and then back out of each one of those surfaces. So what's our net flux leaving that enclosed volume? Well, it's 0, all right? Another example. Let's say I've got a solenoid. Now I'm going to draw this relatively small because I'm going to focus more on the magnetic field it makes. So let's say you got some wires wrapped around this thing like so. And let's say the current's going that way. Okay, round and around that solenoid. Okay, if you do your second rule, your magnetic field will point up as it goes through the solenoid. It'll look like this. All right, so there's our magnetic field, okay? Now you also will get some wrapping around. So I'll draw like one on each side. It'll be much weaker. Okay, so here would be the part, and then it would wrap around like so, okay? And it would go like that. Looks like big ears or something. All right, and the same thing, I'll draw an analogous one on this side. Now again, people tend to focus on those, and they really shouldn't. Those fields are very weak compared to the field inside the solenoid, but hey, we'll go with it. All right, so let's say anywhere in this figure, anywhere you want, we draw any three-dimensional shape. So I'll just draw a blob. Here's a blob, all right? Imagine it's a 3D blob, all right? What is the net flux leaving that red blob? Well, you'll notice I have 4 field lines entering that blob, and I have 4 field lines leaving that blob. So what's our net flux leaving that blob? Well, it's 0. Okay, so it turns out that Gauss's law in magnetism, when you integrate B dot dA, the net flux leaving any enclosed surface is always 0. All right. Now, that's because magnetic fields circulate, okay, and magnetic poles, as far as we know, and we've always observed anyway, always come in pairs. So like here is a north pole of this magnet, and here is a south pole of this magnet. Charge is different. You can have a positive charge, and you can have a positive charge making a net flux outward. You know, I can sit here and have a little positive charge, and it makes an outward flux, right? So if I draw a Gaussian surface around that, you're going to get a positive answer, right? Or if I had a negative charge in there, it makes an inward field and makes an inward flux. But for magnetic fields, they always circulate, and poles always come in pairs. So you can't ever isolate a magnetic pole. So you're never just going to have a north pole by itself. It's always accompanied by a south pole. Therefore, the net flux leaving any magnetic flux leaving any enclosed surface will always be 0. All right, we'll use that fact in a couple of our problems, by the way. So I hope that video was helpful, and thank you very much.